Thank you, Mr. Chairman. My name is Takeshi Yasui in Tokushiba University, Japan. Today, I will present the enhanced sensitivity of refractive index sensing optical cone by frequency multiplication based on the terahertz cone. Go to backgrounds. The refractive index or RI is an important physical quantity of material. Therefore, there is a considerable need for RI sensing in the field of the evaluation of industrial product, gas sensing, biosensing, and so on. So the one representative fiber RI sensor is a multimode interference or MMI fiber sensor, like here. The MMI fiber sensor is composed of clattless multimode fiber together with an input and output single mode fiber at both ends. The incident light is diffracted, repeats the total reflection, and go towards the output FMS, SML. Only the light satisfying the MMI wavelengths, lambda MMI, given by this equation, can pass through this fiber sensor. Furthermore, due to the RI dependence Guss-Henshin shift at the boundary between sensor surface and the liquid sample, or the MMI fiber sensor cause the RI-dependent optical spectral shift like here. So the MMI fiber sensor can work as the RI-dependent tunable or optical bandpass or bandstop filter. But the RI precision is often limited by relatively broad spectral bandwidth and or limited optical spectral resolution of instrument. One promising approach to enhance RI sensing performance, to further enhance the RI sensing performance is the use of the electric radio frequency measurement or RF measurement. This is because the RF measurement benefit from high performance, cost-effective frequency standard and measurement instrument, achieving the high precision and wide dynamic range in RF region. If so, such a RI-dependent optical spectral shift can be converted into the RI-dependent RF shifts. Refractive index can be determined by RF frequency measurement with high precision and wide dynamic range. To this end, we focus on the use of the optical frequency cone for OF to RF converter by placing the MMI fiber sensor inside the fiber OFC cavity, namely RI sensing OFC. Next slide shows the principle of operation for RI sensing OFC, like here. The typical configuration is like here. First, the sample RI change causes the RI-dependent optical spectral shift of OFC by intercavity MMI fiber sensor. And then this RI-dependent optical spectral shift is converted into the RI-dependent shift of optical cavity length, NL. So here, by dispersion of refractive index in the cavity fiber. And finally, the sample RI change can be read out as the FREP given by this equation. In this way, the MMI fiber sensor can work as a FREP reading RI sensor. In the previous research, we confirmed the RI-dependent FREP shift for the water ethanol solution with a different RI value. Like here, importantly, the RI-dependent spectral shift is significantly larger than the spectral line width of FREP signal at the 43 MHz. As a result, we confirm the good relationship between sample RI and FREP shift, like here. But to further enhance the RI sensitivity given by this slope coefficient, increase the FREP shift or delta FREP still remains around the several tens hertz in the FREP measurement of 43 MHz. To further enhance RI sensitivity given by this slope coefficient, increase of delta FREP is required by using a harmonic component of FREP, namely MFREP signal. But the output light of this RI sensing OFC is detected by first photodiode. The the resulting outlet comb remains the MF around the several gigahertz due to the spectral bandwidth, electric bandwidth of photodiode. However, if the photoconductive antenna is used for the detection of OFC in place of the photodiode, the MF achieve over 100 gigahertz because of the use of terahertz comb. So in this way, the key to enhance the RF sensitivity is the use of terahertz comb. Next slide shows the spectral behavior of optical comb and the terahertz comb. When the output light of RF sensing OFC having a frequency spacing of FREP is incident into the photoconductive antenna or PCA, a series of harmonic components of FREP is generated in the PCA, like here. Since the spectral bandwidth of the terahertz, namely this is a terahertz comb. The spectral bandwidth of terahertz comb is extended over the 100 gigahertz. So the MFREP also, the resulting M value is achieved over a few thousand. Then we next the case that RI change cause a delta FREP. So from FREP to delta FREP plus delta FREP. The corresponding terahertz comb is also changed from MFREP to MFREP plus M delta FREP. From the frequency difference between them, we can obtain the M delta F signal. In other words, the delta FREP is multiplied by M. But how we can read the MFREP signal in terahertz region? The answer is given by heterodyne photoconductor mixing in PCA, like here. In this case, the photoconductive antenna can work as a heterodyne mixer between the local oscillator of serial terahertz wave having a known frequency of F terahertz and measured signal of terahertz comb induced by the RF sensing OFC. Right shows a corresponding spectral behavior of them. When the serial terahertz wave and the terahertz comb is incident into the PCA, heterodyne photoconductive mixing between them is occurred. This results in generation of a group of bit signal between them in the RF region, like here. We here focus on a bit signal at the lowest frequency, namely FB bit signal. This FB bit signal is generated by mixing between the serial terahertz wave at F terahertz and M order mode of terahertz comb nearest in frequency to the serial terahertz wave at M FREP. So the FB is given by this equation. Next, we consider that the sample RI change causes delta FREP. The cause change of FREP by delta FREP. So in this case, FB signal is shifted by delta FB. As delta FB is exactly equal to the M delta FREP, we can obtain the M delta FREP by measuring the FB and delta FB in the RF region. Next slide shows the schematic drawing of experimental setup. The RI sensing OFC has a linear fiber cavity composed of the pumping laser diode, sesame, EDF, single mode fiber, MMR fiber sensor, and output coupler. The resulting output light has FREP around the 34 MHz and a center wavelength of 1.55 micrometer. After the optical amplification with EDFA, the output light is converted into its SHE light at the 0.775 micrometer by SHE crystal. The resulting SHE light is incident into the PCA together with the serial terahertz wave at the F terahertz. The serial terahertz wave having a known frequency of F terahertz is generated by serial terahertz source synchronized to the revision frequency standard, so that we can tune the serial terahertz wave from 75 to 100 gigahertz with a stability and accuracy of 10 power minus 10. The resulting FB bit signal was measured by RF frequency counter and RF spectrum analyzer. We first investigate the tuning of frequency multiplication factor M of FREP by F terahertz. Left compares the RF spectrum of FB bit signal before and after the sample RI change. We here use water ethanol solution with a different RI. We confirm the good signal to noise ratio of RF spectrum over the 50 decibel. And then, so the sample RI change causes shift of M delta FREP of 212 kilohertz, like here. As the FREP is this value, the M was achieved to the 3100 when the F terahertz value is set to be this value. We repeat the similar experiment with a different F terahertz value. The resulting relation between F terahertz and the frequency multiplication factor M is given here. A good linear relationship was confirmed between them. In this way, the terahertz function as a linear frequency multiplicator. Also, the multiplication factor can be selected by F terahertz. Finally, and then so we perform the RI sensing of ethanol water solution with a different RI value. Upper graph compares the RI dependent spectral shift between the FREP measurement and the MFREP measurement. So it's important is the ratio of the RI dependent spectral shift to the spectral line width in the MFREP measurement is larger than that in the FREP measurement. Lower graph shows the resulting relationship between the sample RI and the delta FREP in the FREP measurement and MFREP measurement. Here, the RI sensitivity is given by this slope coefficient. So, from the comparison between them, the RI sensitivity was enhanced by 3100. Finally, we discuss the influence of counter limit in RI sensing OFC. Left compares RI deviation of FREP with a counter limit in the FREP measurement of 34 megahertz. In this case, at the short target time, these two plots are almost overlap to each other. In other words, the counter limit is a bottleneck of enhanced RI resolution in rapid measurement. On the other hand, in the MFREP measurement, the alarm deviation of MFREP has a large margin to the counter limit. So higher RI resolution is achievable without being limited by the counter limit. Finally, we summarize the present talk using these slides. Thank you for your kind attention.